Good morning. I hope all of you are doing well. I am Neda Sayahi, a PhD student in ISC department, and I really appreciate that you provide us with this opportunity to present our work here. Today, I will go over my work that I'm going to present in Inform's annual meeting in Anaheim, California. Before I start, I would like to mention something. The reason that my poster is too wordy is the Informs committee of poster presentation section prefer to have a detailed description of our works. So that's why it's too wordy for the sake of those who want to check them out online. My study is titled Predicting Scan Quality, a comparison of machine learning models. First, I'm going to give you a short summary of this study to make the whole frameworks clear. X-ray computed tomography is a relatively new technology in manufacturing metrology, despite its widespread use in medicine. CT scanner now make it easier to acquire complex shaped part in manufacturing, so its use is becoming more common and popular. The feasibility of the scan depends on the setup parameters which CT scan are performed with. Currently, there is no established model that can describe the relationship between CT scan setup parameters and scan feasibility. In practice, CT scan users choose setup parameters intuitively, and this process highly depends on operator's experience. The high operator reliance of parameter selection may result in human errors and delays in scanning process. Here, we argue that by removing the necessity for manual parameter selection, ML methods can speed up the parameter setting process. Given a set of parameters, the accuracy of four machine learning methods in predicting scan feasibility are compared in this study. And the results show that the multi-layer perceptron predicted scan feasibility with high accuracy and outperformed the other methods. And finally, a content-based recommender system was also developed to recommend a scan parameter based on the MLP model result. Having said that, the objective of our research is to shorten CT scanning setup by suggesting an ML-based recommender system that recommends scan parameters based on material feature. Now I'm going to present this study in more details. As I said, the accuracy of CT scan measurement is greatly affected by the object's property, like geometry, material density, thickness, and like any other properties, as well as the scan parameters. So we have object properties and scan parameters. We cannot change the property of the scan, but property of the object, but we can modify the scan parameters. As a result, selecting appropriate scan parameters is critical for the effective use of a CT scanner. In practice, scan parameters are frequently set manually based on objective assessment and the user's personal experience. And the parameter selection process is highly dependent on the operator and lacks traceability. However, there have been few studies to address this issue. The objective of this study is to reduce the CT scanning setup time by proposing ML methods for addressing the following questions. The first question is, given the material properties, what are the appropriate CT scanning parameters? And the second question is, which model is better at determining such parameters? Using a Wenzel, this one. Using a Wenzel America Exact S scanner, the proposed solution will be tested and validated. To answer those questions, we use a data set which was designed with 6 similar L-shaped objects made of different materials. And the scan performance of each object was assessed using various scan parameter settings. 1620 observations were collected, with 80% used to train the data and 20% used to validate the model. Each observation contains 2 material features, which are material density and parts thickness, and also 4 scan parameters value, which are filter number, voltage, current, and integration time. And a binary scan feasibility, which is either 0 means the scan is feasible, or 1, which means the scan is infeasible. 4 machine learning methods were implemented in this study as some of the most popular machine learning methods that have not yet been tested in such applications. We implemented 2 tree-based models, which are decision tree and random forest, 1 support vector machine, which is goal is to find a hyperplane in an n-dimensional space, and n is the number of features, which is 6 here. 4 part features, 2 parts feature, and 4 scan parameters. And that's classify the data point. And the last but not least model was the multi-layer perceptron. MLP models represent the relationship between input features such as material properties and scan parameters in our study, and outputs such as scan feasibility. In figure 3, you can see an architecture of a 4-layer MLP. For the first 3 layers, ReLU activation function, and for the last layer, sigmoid activation function were used. And as for optimizer and loss function, Adam and binary cross entropy were utilized respectively. In this flow chart, you can see a content-based recommender system. Let me just zoom in a little bit. In the first step, we use a multi-layer perceptron result to design the recommender system because it outperforms other methods result. In the second step, we ask the user to provide their material features, including density and thickness. In the third step, among the data set, we find the most similar material features to user input. And then for the similar material that we found in step 3, we find all set of parameters that lead to a feasible scan from the original data set. And in this step, first we save the result in an array and then sort them ascendingly based on the integration time. In step 7, we start from the first row of the array, which has the least integration time, and then we predict a scan feasibility for a scan parameters obtained in the previous step plus the input user. If it's feasible, we suggest it. Otherwise, we will go over the second row and repeat this process. So that's how this recommender system works. In table 1, you can see the performance of all 4 models, and among them, MLP provides more accurate prediction and outperform others, as you can see based on the root mean square error. And also figure 5 shows model accuracy and loss. Blue and orange lines demonstrate train and test respectively, As you can see, model performs the same, on train and test sets, which indicate the model is not underfit or overfit. And here in figure 6, you see that after the user gave us the input, which are the material density and thickness, the recommender system suggests us the some different setting, which is start with the fewest integration time. This item at the end is the integration time. And as you can see, the parameters that the recommender system suggests is sorted based on the integration time, because the less integration time lead us to less CT scan cycle time. For validate this recommender system for future, we are going to design some part and use their feature like density and thickness to test the recommender system. If it works well, so that's good. But if it's not, we will tune the parameter of the recommender system to generalize it more. And this work has been supported by Wenzel Group. Thank you so much for listening to